A couple years ago, I put out a video where I converted a drill press into a milling machine. I've used that for hundreds of projects over the past few years. Doing so, I've learned where the machine's strengths and where its weaknesses are. In today's video, we're going to upgrade the drill press mill. We're going to try and address some of those weaknesses. If that interests you, stay tuned, we'll get started. All right. The first thing I want to upgrade on the drill press mill, I want to change the way the table is mounted to the press itself. Currently, it's supported on the drill press's original table, which is held to the column. So as I move the linear screw up and down, the table rides on the column and that's what holds it. It's locked in place with a clamp here on the column. Because I opted not to bolt it or mount it to the lead screw, and because there's nothing here to hold alignment, you get a lot of movement. That's not ideal. So I would like to remove it so that the table no longer mounts to this round column. My idea is to use a square column and mount the table on a pair of linear guide rails. I'm using some 6" by 6" 3/8 wall square tubing. I went with this because I think it'll be good and stiff, but also it provides a wide enough surface that I can mount linear guide rails to it. The further apart the guide rails are, the more support they'll provide in this direction. This tubing is 36 inches long. It needs to be cut down to 18 to match the maximum travel on the drill press. I'm using my metal bandsaw to cut this to length. This tubing is actually wider than the capacity of my saw, but I've found that if I cut it one side at a time and I rotate it around, that it'll work. I'm using some linear guide rail made by THK to carry the table and maintain its alignment. The guide rail is way too long. So this measures 28 inches. I need to cut it down to 18. I'm just going to use a cutoff wheel and my angle grinder to do that. Once I had it cut to length, I used a belt sander to put an even finish on the end of the guide rail. The 6x6 square tubing I'm using for the column, it's not perfectly flat. It's not the ideal surface for mounting the linear guide rail. So instead of bolting that rail to the column, I bought a length of 6" by 1/2" ground steel plate. This is flat and smooth. It'll be a really good surface for the guide rail. So I'm going to mount that plate to the column, and then I'm going to bolt the guide rail to that plate. So there are 8 segments on this guide rail. So I am going to install a bolt behind it in each one of these locations, kind of like this. I am using some M8 low profile bolts. These have a really shallow head, and I'm doing that so I can recess them into the back plate, but still give me a lot of material to bolt this down. The way I'm going to install these, I'm going to drill through both the plate and the column, the diameter 4 and 8mm tap. I'm then going to remove the plate. I'm going to tap the holes that are in the column, and then I'm going to bore out the holes in the plate, and I'm going to use the end mill to run a countersink. Each one of these linear guide rails is held in place with 16 4mm bolts. They have to be really accurately located. To do that, I aligned one rail with the edge of the plate. I drilled and tapped it and bolted it firmly down. I then clamped the second rail in place and confirmed alignment with a dial indicator. Once I had it correct, I drilled, tapped, and bolted that second rail. I want to be able to adjust alignment between the mill and the base when it's assembled. So instead of welding the column to the base, I'm going to bolt it in place. That will allow me to make fine adjustments using shims. I made the flange for mounting the column to the base using some 1/2" steel plate. I cut it down to 8 inches square and I drilled 1/2" holes in each corner. Those holes will bolt it down to the base. To maintain alignment between the column and the base, I bolted the new mounting flange to the base. I then aligned the column with an angle finder and bolted it down with a chain. When everything looked good, I fully welded it in place. Once welding was done, I used a needle scaler to remove slag and to put a nice finish on the flange. I'm going to make the new table out of some hot rolled steel. I've got a lot of this stuff laying around. I bought it in the past for other projects that didn't pan out. There are a couple of big problems with using hot rolled steel though. The first is mill scale. This stuff is covered in a hard coating that is formed when it's made. It's incredibly difficult to remove. The other is that it's not very square. So this is a 12-inch by 6-inch piece. It was cut with a shear, so when they do that, they tend to bend it. So if you look at this, it's got a bend on the end. And then because it is made by rolling it between rollers, it tends to have a wave to it. So if I put a square here, you can see that rock. So to use this, we're going to have to remove that mill scale, and then we're going to have to square it up. So here's how the table back plate turned out. I used a 3-inch fly cutter to get it flat, and then a 2-inch shell cutter to mill the edges to clean those up. This is going to bolt to the linear guides, kind of like so, and then will support the rest of the table. So the table will bolt to this, and then this bolts to the guides, and then our work table will sit about here. These are the guides I'm using. They've got 6 bolts per guide, and there's 4 guides. So that's 24 bolts that I'm going to have to drill holes for to mount the table. That's a lot of bolt holes to get in the right spot. I could manually measure these, lay them out, and punch each one, but I run a real risk of getting some of these in the wrong spot, and if I do that, it's going to make a real mess. So instead of doing that, I carefully measured the bolt pattern, and I drew up this guide in SolidWorks and then 3D printed it. This let me confirm that my measurements were correct, and now I've got a plate that I can use as a jig when I drill the back plate. So this jig is made from PLA plastic. Once you start drilling, the heat and the chips will melt it. It's not a big deal though, because at that point you've already got the hole started and the jig doesn't do much. So here's how that table turned out. I was able to mill it flat using a 3-inch shell cutter. You can see where the welds are. So these were the holes that I welded shut. The welds are harder, so when the cutter ran over them, it resulted in a slightly different surface finish for the welds. If we flip this over, looking at the back side here, I milled out a couple spots. So this back portion will allow the back plate to bolt and be square. So I machined that out so I get a good fit there. And then this center portion will carry the mounting bracket for the linear screw. So this is going to bolt in place here, and then the screw will thread on and be attached to this point. I'm going to bolt the table together instead of weld it. The reason being that I went to a lot of trouble to mill the table to get it square. If I weld it, it's going to distort, it's going to no longer be square. So if I bolt it together, I don't have to worry about that. This table is going to be bolted together in 3 places. So I'm going to start by bolting the top to the back. Once that's done, I made a pair of ribs, and I'm going to put these ribs in place, and they're going to be bolted to the top and then to the back. So I've got this set up here, kind of an odd arrangement, but I think it'll work. I'm going to use the mag drill. We're going to start, and we're going to drill the back here and bolt the top to the base. So I've got the new column now mounted to the stand, and I have fitted the work table. It's bolted in place. What I need to do now is I need to tram this head to the table. Because this is a new table, these two aren't necessarily square. I drilled and tapped some holes in this square column, and I threaded in some bolts. Those bolts squeeze or clamp the round column in place. So I've fitted a dial indicator into the chuck, and my plan is to sweep that dial indicator across the table and then use these bolts to change the position of the round column until I get the same reading in all points on that dial indicator. When that happens, I will know that the head is then square to the table. All right, so I think I've got this just about right. As I swing the dial indicator around, I've got about a 10 micron swing between the 3 corners. I don't think I'm going to be able to get any better than that with this table. So now that this is aligned and it's trammed and I'm happy with it, I am going to fill the column with epoxy. So I'm going to mix up an epoxy sand mixture. I'm going to fill the square column and the round column, and that mixture will pretty much turn this into a solid piece. I'm going to fill this column with epoxy granite. I found a video by Metal Musings. His best recipe used epoxy, gravel, and dust from his sandblaster. I don't have the dust part, so I'm substituting some steel abrasive media. This is more coarse than I expected, but I think it'll still work. I'm using a recipe that is 50 pounds of steel grit, 16 pounds of gravel, and half gallon of epoxy. So this mixture added 67 pounds of weight to the column. I am using 1-to-1 tabletop epoxy. I went with this because I've used it in the past and it's really cheap for what you get. To make sure that everything is mixed correctly, I mix the epoxy in one bucket and the grit and gravel in another. And then I poured those two buckets together and mixed it until I had an even consistency. To fill the column, I found what worked best was just to scoop it out by hand and push it into the column. I filled both the square and round columns with epoxy. It feels really stiff, and I also think it's going to be good at damping vibration. If I take a metal tip on this screwdriver, it does not ring like a bell. So I'm eager now to get the head on this and see if I'm going to get the results I expect. The second upgrade I want to make is I want to replace the head. There were a lot of comments in the original video that pointed out that this Walker Turner head wasn't ideal. So I am going to replace it with this one. This is a Rockwell 15-inch drill press head. It's got a lot of advantages over the Walker Turner. The spindle does not stick down as far from the main casting, so it'll have more support, should be more rigid. The second, the casting is a lot larger and it's hollow, so it should be more rigid and I can fill it with epoxy. And then the third, the quill is quite a bit larger on this machine than it was on the Walker Turner. So I can actually fit tapered bearings into this spindle, whereas this one I could not. So replacing the Walker Turner with the Rockwell I think is going to be a good solution. Before I can fill the head with epoxy sand, I need to clean it up so that the epoxy will stick. There's about 60 years of grease and grime in this thing and I got to get that out. I started by giving it a bath in mineral spirits, using a lot of brushes and even a screwdriver to get it clean. The mineral spirits did leave a residue inside, so I cleaned that out using some brake parts cleaner. This head casting is completely hollow. We can't just pour epoxy sand into it, or it would get in where the quill goes and it would run in where the column goes. We've got to isolate those. So to do that, I cut some dividers out of some thin sheet metal. I shaped those to fit around the internal contours, and then I held those in place with some JB Weld steel stick. This stuff works really well because you can push it in place and then it sets up rock hard. To ensure that the steel stick was completely epoxy tight, I mixed up a small batch of epoxy and I brushed it over top. That way, when it's fully cured, I know there's no chance that the epoxy sand will leak out. The epoxy sand mixture I used in the head differs quite a bit from what I put in the base. I didn't have any more of the steel grit, so in this one I just went epoxy and sand. So here's the recipe I used. For epoxy, I used 64 ounces per batch. That's 32 ounces of resin and 32 ounces of hardener. For sand, I used 16 pounds per batch. That gave me a mixture that was about 20% epoxy and 80% sand. I'm using play sand for the sand in this mixture. It's got some moisture in it, so to dry it out, I put it in my toaster oven and I baked it for an hour at 450 degrees. That ensured that there was no moisture left in that sand. I started by mixing the epoxy and the sand in separate containers. Once they were well mixed, I brought them together into a single bucket and mixed them again. I found that the best way to fill the casting up with epoxy sand was just to scoop it up and push it in by hand. Once I had the casting filled with epoxy sand, I tapped it with a mallet to try and work out any trapped air. This caused the sand to settle a bit and some of the epoxy rose to the surface. To match the paint on the rest of the equipment in my shop, when the head was fully cured, I masked it off and I gave it a coat of Rust-Oleum gray. The original bearings in the spindle in this machine were Norma 203 KPs. These are shielded on one side and sealed on the other. These were in good shape, so I was really careful when I removed them not to damage them. I replaced those with a pair of FAG single row angular contact bearings. These bearings, the replacements, are not sealed. The price difference between unsealed and sealed angular contact bearings was significant. A few $100s for both bearings. The preload on these original bearings is established with a wave washer. The original wave washer was getting pretty soft, so I ordered some replacements from McMaster Carb. These wave washers have a slightly higher spring rate than the original. I'm hoping that will add additional preload to these bearings. As I mentioned, the original bearings were sealed while the replacements are not. So I need a way to seal the spindle so that the chips don't get in and the grease doesn't get out. I designed and printed some seals that fit tightly into the bore on the quill. They're made out of TPU, so they're flexible, but they should also tolerate any heat generated in the bearings. These seals fit well and should do a good job of protecting the spindle bearings. I'm using the same motor on this machine that is on my round column mill. This is a 1 horsepower 3-phase motor. This one is made by Reliance Electric. It's their XEX or their premium efficiency motor. This one I like because it's got a full cast iron housing. I purchased this motor specifically because it is a 3-phase motor. We need a 3-phase motor to work with the VFD. I got the new drill press mill put together last night. There were a number of upgrades I made while I was doing that I want to show you guys. Once that's done, there are some projects I set aside that I think will be really good for trying this machine out. So let's take a look at those upgrades I made and then we'll see how the mill performs. The first thing I want to show you is the shroud. So this is the original Delta shroud. Cleaned it up and I painted it. I am using a pair of stepped pulleys and a belt to drive the spindle. These were 5-step pulleys that I got on Amazon. I went with 5-step because they were cheap. The 5-step though did not fit inside the shroud, so I put each one of these in the lathe and I turned off the largest pulley. I kept the pulleys because even though I'm using the VFD, the motor doesn't have a lot of torque at really low RPM. By keeping the pulleys, it allows me to change the initial speed so I can still get that torque. I wanted to install a tachometer on this machine so I know exactly what the spindle speed is, but I wanted that tach to look like it belonged on the machine. So I took this switch, I pulled the guts out of it, and then I drew up this new switch plate. So now I've got one plate that holds the switch and the tach and looks like it belongs on the machine. It is absolutely critical that I keep chips out of those linear guides. So instead of using a flexible chip guard, I wanted something a little more substantial. I used 3 1/8-inch thick plates of aluminum. I slotted those and I made a rigid chip guard that moves up and down with the table. So as the table is moved upward, the chip guard acts kind of like a shutter and it keeps chips out of the linear guide. The new table is quite a bit heavier than what was on the drill press before. I had originally had a little 3-inch handle on the screw jack, but with the heavier table, it just didn't have quite enough leverage and it was difficult to turn. So I pulled that off and I replaced it with this 8-inch wheel. This is quite a bit nicer. It's really smooth and easy to turn, but it also makes it easy to make fine adjustments to the Z-axis. A problem I had noted when I did that is that this table has a tendency to move down with the weight of the table. So to lock it in place, I built a lock here that clamps onto the other side of the screw jack. When tightened down, it basically locks this handle, which locks the table. Because the table on this machine can move up and down, I needed to know exactly where it is. So I added a DRO to the Z-axis. This allows me to see exactly where the table is in relation to the head. The last thing I did is I rebuilt the table. So I pulled it apart, I cleaned it all up, I polished the ways, I recut the T-slots so that the T-nuts would actually fit in there and move smoothly, and I recut the ends of the lead screws so that the thrust bearings actually set flush and square to the screws. So now when the handles are rotated, I'm not getting near that wobble that we used to have. I also upgraded these locks. I got rid of those wing nuts and I used some adjustable locks. The table now feels a whole lot nicer to use. It's really smooth, it doesn't have the backlash that it used to have, and the handles don't wobble when you turn the screws. I want to take a quick moment to talk about how we hold milling tools in this drill press. So this machine has a JT33 tapered spindle. Rockwell actually made a number of arbors that will support different tooling for this machine. These are the arbors I've managed to collect. Each one of these was made by Rockwell. The first one, this is 15837. This tool will hold anything with a 1/2 inch shank. It's got a pair of set screws that engage the tool and hold it firmly in place. It works perfectly with a 1/2 inch end mill. The flat is in exactly the right spot for the set screw. So I can use this one for any tooling I want to use. It's got a 1/2 inch shank or for 1/2 inch end mills. The second one, this is a 1/2 inch arbor. It's threaded. So this is Rockwell part number 15835. Because it's got a 1/2 inch threaded arbor, I can put on anything with a 1/2 inch bore. So if I want to use a slitting saw or I want to use a cutoff wheel, something like that, anything that will fit this 1/2 inch arbor can be used with this one. And then the third one I've got, this one is actually branded Craftsman, but it's made by Rockwell. I don't have a part number for it, and this one is the rare one. This is the one that's hard to find. But this one uses a series of collets, and you can use any size end mill in this one that you've got a collet for. So I've got a 1/4 inch, 3/8, a 1/8, and a 3/16 inch collets. So this tool will hold a 1/2 inch end mill on down for each one of these collets. So between all this tooling, I can hold pretty much any milling tool that I want in this machine that this machine would really be capable of running. Here's a couple projects that I think will work out well for trying out the mill. So the first, these are bicycle disc brake adapters. These align the caliper to the frame. A common problem with these, especially these cheap ones, is that the face tends not to be square, and it also tends not to be parallel. So what I want to do is I want to see if I can recut these faces and square them up. So let's start with these disc brake adapters. I'm going to take one back over to the mill. We'll get it put in the vise and we'll see how it works. Here's how those disc brake adapters turned out. This machine worked great for getting them square. These turned out so well that I went ahead and I did the same thing to all the adapters I own. That way I can put them in my parts bin, and when I need them, they're ready to go. The second, this is a spare head for my tripod. I don't use this one because it's not well made. It's not the same width all the way across, and it tends to bind when used. So I want to see if I can recut this face here, square it up so that it actually works and slides like it's supposed to. I switched over to a 3/8 inch end mill to cut the new faces on the tripod adapter. The wobble you see here is an illusion. It's caused by the shutter speed on the camera and the LED lights. In actuality, the mill is running true. The machine did a great job with that. The faces are now parallel and the adapter fits perfectly into the tripod. So these are the kind of projects I expect to use the drill press mill for. Anything more involved, either a harder material or I have to remove more material, I'll take the time to set up my jet mill and I'll use that. So the drill press mill really will never have to do anything more difficult than this. That being said, you may not have another mill. So let's put this one through some harder projects and see how it does. I'm going to start by squaring up a piece of hot rolled steel. Once that's done, I do have a fly cutter with a 1/2 inch shank. So we'll put that in the machine and we'll see how well it faces aluminum and steel. And then I ordered a small slitting saw. It's not something I typically use, but I've got the arbor for it. So we'll fit that to the machine and we'll see how that works. This is a 3/4 inch piece of hot rolled steel. I'm using a 1/2 inch carbide end mill. I put the depth of cut for each pass on the screen so you can see how much material I'm removing. I've sped this up, but I've kept the entire process. I want you to see how many passes it took to cut down this steel. On this machine, the best I could do with an end mill was about 10/1000ths depth of cut. Anything more than that and the spindle really started to make some noise. So it took something like 10 passes to get this flat. If I was doing it in my round column mill, I would have done it in a single pass. So far, I've only used end mills for face milling. I want to see how they do when they're side loaded. So I've loaded up a 3/8 inch end mill here. Let's go ahead and cut a groove all the way around the perimeter of this aluminum. Side load this end mill, see how it does. That smaller end mill actually did a better job than the larger one. I was able to remove more material and the surface finish was better too. So now let's see how it does with the fly cutter. So this is a really cheap fly cutter I got on Amazon. I got this one because it was the only one I could find with a 1/2 inch shank. That fly cutter did such a nice job on this side. Let's flip this over, we'll do the other side too. The fly cutter did a much better job on the aluminum than I was expecting. So now I want to put the hot rolled steel block in here, machine the face and the edge of it with a fly cutter and see how it compares. I thought the fly cutter was going to be the worst performing tool we tested, but it did a really nice job on both the aluminum and the steel. I'm really impressed with how well it worked on this machine. The last thing I want to test on this machine is the slitting saw. I don't use these often, I typically just use a hacksaw, but I want to see how this one does. I didn't realize with the slitting saw that I need spacers to center it in the arbor. I don't have time to make those and I don't have anything that'll work. So I've just fitted a spacer here to move the slitting saw downward from the arbor, but you'll notice as I use it that it's not perfectly centered. It's got a little bit of side to side movement. I think it's all right. I think we can still test it and see how it performs, but that is something I will have to make in the future if I want to use this tool. The kind of thing I would typically use a tool like this for is slotting holes so that I can use them for clamps on shafts. For the mill build itself, I could have used a tool like this for clamping the Z-axis. So this is just some junk part I pulled out of my scrap bin, but I'm going to take the saw and I'm going to slit it through so that there's a slot between the outside and the inside of that hole. Kind of part that could be used for a shaft clamp if I happen to be making one. So you can see the saw is not perfectly centered in the arbor here. So keep that in mind. You'll see a wobble to this saw, and that really is there because I don't have it perfectly centered in the arbor. So here's how those turned out. Had no trouble at all on the aluminum, really nice surface finish, and the deepest cut I did was about 1.5 millimeters, and it had no trouble with that. The steel was actually the same story. I didn't have a piece of steel that made any sense to put a slot in, so I used just this scrap hot rolled steel, and it cut right through that just fine too. Same performance, honestly, as the aluminum. I'm really happy with how this machine turned out. It works even better than I had hoped it would. The changes I've made, it's a much better machine than the Walker Turner was, even when the Walker Turner was set up as the mill. I mostly put this together to use for precision drilling. I often have projects where I need accurate or precise holes, and setting up my round column mill for a drill is kind of clunky. Since I got that round column mill, I haven't had much need to use a drill press as a milling machine, but having a second machine that is capable of some light milling, I think is going to be really helpful around the shop. If you're converting your drill press into a milling machine, or you're putting together a drill press for a small milling machine, the two big takeaways from this video are: buy a head or look for a head with a really large quill and really large bearings. The larger the quill, the larger the bearings, the more capability as a milling machine the machine will have. And the other is focus your time and attention on the table. Make the table as rigid as you can. Rigid table and big bearings in the spindle, and you'll have a machine that's a lot more capable. So if you're curious what happened to the old Walker Turner after I stole so many of its parts for the new machine, I bought some 2 3/4 inch DOM tubing and I bored out the head to fit, and I turned it back into a floor model drill press. So now I've got a drill press that I can use for anything I need it for. I can drill wood or metal or plastic or whatever. It's just a good all-around general drill press that I can use to drill a hole quickly. So it didn't end up in the scrap bin. I didn't give it away. I just turned it back into a drill press and back into a good usable tool. The more observant amongst you may have noticed that my appearance has changed quite a bit between the start and the end of this video. That's because it took me about a year to build this machine and to put the video together. I didn't work on it full time. I worked on it when I had chance, and there was a full writing season between when I had built the table and when I put the head together. So the me at the beginning of this video is about a year younger than the me right now. So I really enjoyed making today's video, even though it did take me a year to put together. I hope you enjoyed watching it. Hope you got something out of it. Until next time, I'll see you later.